Okay, so now let's get more interesting as by way of an example. So I went ahead and drew out some stuff. We're going to fill this in, but let me explain what I've got. I've got an incoming soccer ball. Here it's coming inwards towards the left. Here's a soccer player. The little foot that's got a circle on it, that's the kicking foot, so you can follow it through. So here is before the kick. This is some moment in time during the kick, but you know, the kick actually takes a little bit of time. You could say that the kick itself takes a 20th of a second or something, depending on, you know, who's kicking and what the, details of the kick. But that is a instant in time during the kick, right? And then this is after the kick. So you can see that the little kicking foot, the circle, is on the other side. So that's the follow through of the foot. So it follows through to the other side. And then that's the outgoing ball. So the ball on the way in is headed purely leftward. At this moment in time, I didn't draw any motion for the ball because I actually don't know. I don't know what the motion of the ball instantaneously right there is. It could still be heading this way, but it could be on the way out. I just labeled a moment in time during the kick. In this case, though, this is after the kick is finished, but before the ball has gone too far into the projectile motion, because you know that ball is going to go up and come back down. I don't care about this part. I only care about right after the kick. This is right before the kick. The ball is cruising along the ground. This is right after the kick at the beginning of its projectile motion. It's heading purely leftward here, but I gave some details about how it's moving after the kick. It is heading now rightward, but as well as upwards, as well as into the page somewhat. It's heading kind of like this complicated three-dimensional direction. Because in general, you know, soccer games happen in 3D. They don't just happen in 1D or even just 2D. It's really 3D. So if it's 3D, then imagine the force onto the soccer ball to change its motion from being leftward to being rightward, upward, and inward all together. So the force must have been in the x direction to change it from left to right, in the y direction from changing it from no y direction motion at all into having some upwards motion, and then in the z direction as well. In the z direction, you had to kick it into the page. So there needs to be some z direction stuff. I also labeled the fact that rightwards is, I didn't do it explicitly, but that's the positive x direction. Upwards is, we'll call it the positive y direction, but into the page actually is the negative z direction. The positive z direction points out. The negative z direction points in. I did this because I really wanted to have a negative amount of force somewhere in there so that we could talk about something. Okay, so I've gone, and we've described that we require force in each of the directions. So the force on the ball by the person is a vector, and it is time dependent, because before the foot is in contact with the ball, the force is actually 0, right? But then, as soon as the contact starts, the force doesn't immediately get very strong. It ramps up. It has to grow up to some really large value, and then it begins to leave the foot and come off the contact with the foot, so the force goes away and back down to 0. And you can see that this is kind of complicated, and it depends on the kick, it depends on the player, it depends on the soccer ball, it depends on lots of things. But nonetheless, it's got some shape like this. This is what it's going to look like qualitatively, right? Somewhat semi-mathematical and somewhat conceptual. The y direction is similar, but I'm going to draw the y direction force a lot smaller, and it's going to be kind of weird. This t sub k is meant to be the same time, you know, on somebody's watch watching the game, and t sub k, so I'll turn on the y direction force at the same time, but I'm going to extend it and make it small, so it's not as strong, and I'll show you why. And it happens over wide time. If you think about kicking a soccer ball, when you kick it, here it comes. In some sense, you catch it, it smears and deforms into your foot, and you carry it for a bit, and then you press it away, redirect it and press it away, right? So this is us redirecting and adding a little y direction motion or y direction momentum. This is impulsing into the y direction. And then this one, though, I go into the page, so this one needs to be like that instead, or something. So it's negative. Okay, so you can see that I could imagine integrating this f sub x in time from the moment it turns on to the moment it turns off. And it's centered around t sub k. And here I could imagine integrating f sub y dt, also from on to off. And here is the integral in the z direction, dt, from on to off, like that. And when I do this, it'll be the impulse by the kick in the z direction. This is the impulse by the kick in the y direction. And this is the impulse by the kick in the x direction. F net, though, on the ball, if I know what F net is, I can tell you what the change in the momentum of the ball is. So I'd like to point out that these right here are the force on the ball by the person, but this is not F net. Big deal. F net is more like, and it depends on what you want to model. If you want to include friction or air drag or anything else, then you have to go and do a little bit more work. But a realistic model includes the fact that gravity is everywhere on the soccer field. And so really the net force is the force on ball by the person plus the force by gravity, which is called the weight force. So if I want to know Jx net, then I need to use F net in the x direction integrated over time. This is delta P in the x direction. In this case, F net x, W has no x component, right? The weight force is down. The soccer ball is heavy downwards, not in the x direction, not left or right. So actually, there is no W here, and so F net x in this model of the net force, F net x is just the force on the ball by the person. But in the y direction, this is where W will show up. W is not in here. So I'll put yes, W, no, W, no, W. All right, we're thinking conceptually, semi-mathematically. There is definitely integrals in here, and that's even still semi-mathematical. Okay, so let me continue with this. I hope my phone doesn't die. Incoming ball's to the left. Outgoing ball is towards the right, up and in. Incoming momentum is towards the left. The outgoing momentum is towards the right, a little bit upwards, but also a little bit in. And I've made P final kind of big. That is, it's a large magnitude of momentum compared to the incoming, say, slow soccer ball. Vectors PF minus PI is delta P, right? And in vector language, also Impulse Momentum Theorem says that that is the net impulse. So with vectors, though, we have to be really careful. jnet equals p final. I'm going to add, because what I know how to do is add vectors, but I'm going to add on the opposite of the p initial vector. So this is what p initial is. So this must be what negative p initial is, right? So I'm going to use vector addition to figure out what is the net impulse. So I've got p final. Let me redraw it. There it is. It's up, in, and rightward. And then I add on negative pi. I don't add on pi, I add on negative pi. So when I add, this is the tip to tail method of adding on minus pi. This is pf. The sum is this dashed line. That's the sum. Yeah, so jnet is pf plus the opposite of pi. That's the construction. This is jnet. It's big. The point of me saying that is when stuff bounces, you see this big jnet? It's because of a really large change. It's a change from left to right bouncing.